So, to account for the radiation, what we do is, as I said, the surfaces by comfort condition also will depend upon the surface temperature, because the surfaces will radiate heat, right. Now, this is taken care of in terms of something called mean radiant temperature. So, it is equivalent temperature of the air, or sorry, equivalent temperature of the surfaces which will have same radiative heat transfer effect onto the body, same as the individual surfaces temperature. What I mean is, every surface will have different temperatures in the room. Some wall will have one temperature, another one will have another temperature, and maybe ceiling will have another temperature. They will have different temperatures in the room, all surfaces. If I have a single temperature to represent, some kind of a, I will not call it weighted average, some sort of a single temperature of all the surfaces, it will produce a radiation heat effect that should be same as that is existing with different temperatures of the surfaces. So, different temperatures of the surfaces will produce some radiative heat transfer effect. I assume a single temperature of all the surfaces that should produce the same effect. So, this is the temperature we should find out. Well, we do not measure it directly, but measure it through a device called globe thermometer. So, it is nothing but you have a globe, blackened globe, right, blackened sphere, and put the thermometer inside. That means, you have a thermometer, put it in a blackened globe. Now, why blackened? Then it will absorb all the radiation. And then its temperature will increase. Because this temperature will be more than the surrounding thermometer temperature, more than the surrounding thermometer temperature, more than the surrounding. Supposing I have a thermometer now. Just another thermometer by the side of it. There is another thermometer, small thermometer here, and we will find that this is somewhat less, this is somewhat higher, because this air here will warm up, receiving all the radiation that is falling onto this globe from the surfaces that is all around. So, the globe thermometer temperature will be somewhat higher than the DBT in the room, dry bulb temperature in the room, because it will take care of the radiation that is coming in. This is blackened surface, all the radiation that is coming in. Now, if the surfaces are almost same temperature as the air temperature, then this temperature will be nearly same. So, Tg, this is called globe thermometer temperature. Tg is this temperature. Now, once its temperature rises, or temperature here is more, as indicated by this thermometer, this will start dissipating that heat, assuming that all air surfaces temperature remaining constant, right. A steady state will be reached after I have put that globe thermometer. Temperature of this one will rise and then stop, it will remain there. Now, at that point of time, whatever heat is being received must be dissipated out, to the surrounding air. So, it receives heat by radiation and dissipates that heat out to the surrounding by convection, and if the air temperature is lower, convection and radiation both. So, that we take care of in terms of Hc, which is the surface conductance of this particular one. So, it actually transmits this heat to. So, equation will be Tg minus Ta into Hc, that is the loss. Tg is higher, and that must be equals to whatever I am receiving. So, Hr, let us say Hr into T mean radiant temperature, the constant temperature, minus Tg, that is what I will be receiving. So, mean radiant temperature is the constant temperature of all the surfaces, that minus Tg into Hr, radiative heat transfer coefficient, and that. So, from this it follows one can actually derive this expression. I am not sure whether I have derived it. So, this let me remove now, this explanation is over. This is the kind of equation that is there. So, Tg, HTg, so it would be Tg from this one Hc, right, and this side also minus Tg. So, if I bring it here Hc Hr must be equals to T MRT Hr plus Hc Ta. So, T MRT Hr plus Ht Ta divided by Hc Hr gives me the Tg. So, this is measurable, Tg is measurable, T MRT is not measurable. This is my assumed temperature of all the surfaces. So, if I have measured globe thermometer temperature, T MRT is taken care of. Okay, I can actually, this is conceptual, more of conceptual, but Tg can be measured. Tg can be measured. Ta is measured, right. So, what we do is, if you want to take the radiation effect into account, then instead of using Ta, I use Tg. Instead of, supposing the surfaces are very warm, surfaces are quite hot compared to the air, then instead of taking Ta, I take Tg. That will take account of the radiation that is falling onto the body also, right. So, thermal comfort is related to Tg. So, if I take Tg, then I have also taken account of the radiation as well as air temperature itself. So, now my comfort condition depends on Tg, relative humidity, and Ta itself would be definitely there, but Ta is already taken care of in Tg. So, Tg, relative humidity, air velocity, type of clothing, acclimatization, adaptation, etc., etc. So, this is what I said, this is the Fangus law which was there, which was there, right. So, KMD HC Tc minus Ta, HR Tc minus Tm plus QCD. So, K is 0.0 to 0.75, that means 25%, 1 minus K, that goes out straight away. Hc is the conductance of the cloth to the air. So, Tc, that convection part, the last part, then Hr is Tc minus Tm plus QCD. So, this is the conduction loss, this is radiation loss actually. So, for resting and this is K is 0.70 to 75 for resting and 0.6 for active condition for thermal comfort condition by osmotic process, and heat loss is about 12 watt per meter square, because various kind of this value, how much is lost from the body before passing through the cloth and skin, because if you remember that model that we did earlier, so some portion of heat goes away straight away, right. This is passing through the clothing, and this same one has to pass through the boundary layer, and my temperature here is clothing temperature is Tc, this is the skin temperature, right. Kqm has to pass through there. So, this K would depend upon how much is being lost, from the body. So, by various mechanism, and that we are saying that it could be something like, Tc was the clothing, Ta is the outside, Hc is that one, and K is depends upon depending upon your type of activity. Some process heat loss is about 12 to 12 meters square. So, condition for thermal comfort condition by osmotic process, loss can be there, and it's about 12 watt per meter square or so, whatever it is. The values are not very important. Above 28 degrees centigrade, evaporative loss through sweating increases and depends on relative humidity. Well, all we are trying to see is the factors which will affect. So, below 28 degrees centigrade, sweating does not occur really. If it is above 28, then loss through, and it will then depend upon relative humidity. QCD is conduction loss, like I am standing on the floor, so loss through the floor, or if I am touching something. Now, the contact area is so small, conduction heat loss, and their temperature difference may not be too large. So, I can actually QCD can be neglected, right. Now, radiation again takes place from Tc, I mean the you know, like C Tc was clothing to the mean radiant temperature. Tm is actually mean radiant, I did not write full MRT. So, this is the radiative heat transfer, mean radiant, right, and this is Tc to air, and this is a surface conductance. So, this is neglected. Therefore, what we are seeing is QMD, QKMD is Tc minus Ta HR Tc minus Tm. So, important issue is this and this etc., and I can write it something like this minus Hc, you know, I can just Hc Tc I can separate out, HR Tc radiative, this I can separate out, and HCTA etc. So, this minus this is the heat you know, the loss of heat is given by this formulae, I mean this sort of formula, and Tc can be taken common, little bit of algebra, and I can write it as QMD divided by Hc plus HR, right. This is the radiative heat transfer coefficient, and convective heat transfer coefficient will be given as Tc minus Tg, because Tg was, remember this was Tg, all that we are trying to show here is then Tg is an important factor. Tg is an important factor if mean radiant temperature is high. If this is same as Ta, this value will become Hc Ta Hr Ta. So, this will become simply Ta. If Tm is equals to Ta, mean radiant temperature is same because the surface temperature is same as the. So, if this is Ta, then this term will be simply become Ta, Tg will become equals to Ta. So, KMD is equals to Tc minus Tg, and summing up, you know, resistance and all that, if I put it, again this is the same sum total of all the fluxes multiplied by the resistance is that body temperature minus Tg. So, it is, you know, layers in series, that model we are applying. QMD is what is generated, part of it passes through the body, rest all goes out. This is the RS was the first resistance up to the skin, this is the resistance of the clothing, this is the resistance from the, you know, skin to, I mean cold clothing to the surrounding atmosphere, and that must be equal to body temperature minus Tg. The surrounding temperature is if the air temperature and surface temperatures are different, and therefore, all will cancel out and all that, that is fine. So, QMD is equals to RS K, you know. So, you can now see what are the factors which govern the thermal comfort. So, it follows therefore that globe temperature shall be given below, maintain the thermal heat balance of the body and hence the comfort condition. So, Tg is important. So, Tg is important, that is what all we are saying. QMD depends upon activity, how much you have generated. K is a function of activity and relative humidity, because evaporation loss is taken care of in 1 minus K. RC is dependent on clothing, RSC depends upon air temperature and air velocity. RSC is from the clothing to the surrounding, So, thermal comfort depends upon your activity, relative humidity, how much it can be lost by evaporation, clothing, air velocity of course is there, and RSC depends upon air temperature and air velocity. So, these are the factors you have seen. So, therefore, main factors again summing up, globe temperature, mean radiant temperature etc., you know, taken care of in the globe thermometer temperature, relative humidity, radiation of surfaces which is again taken care of in globe thermometer temperature, and air velocity. So, these are the factors which governs your thermal comfort. Now, how do I take care of that? I can actually say each one of them. Clothing is equals to 1.5 kilo, air velocity is so much. You know, I can define that your thermal comfort in a room would depend upon air temperature, the surface temperature or mean radiant temperature. So, ranges of those I can define and say this is the comfortable range, depending upon your type of clothing, depending upon also the air velocity. So, all those 4 or 5 factors, each I can give a range, but that will become too cumbersome. What we can do is we can combine all of them into a single index. So, these are called comfort indices. We will use 1 or 2 comfort index. So, comfort index actually combines effect of the radiation coming from surfaces, that is globe temperature, globe thermometer temperature, also the air temperature, relative humidity, air velocity, and might vary from clothing to clothing, right. Additional factors which are not quantifiable easily, adaptation of human being. There are some people who are trying to do research on this line and have been done also, number of them doing in India too. But what I find is they go and survey, talk to people whether you are comfortable in this condition or not, that kind of questionnaire survey. But regression and scientific basis are not, I am not very much convinced, because you find that it's so much of variation, and statistically the research results, some of them which I have seen, I am not very convinced. Of course, it depends upon adaptation, but how do I quantify you? That still remains a question. It is still, how do you generalize and quantify? That is an area of research actually. So, adaptation of human being is very important. You do adapt yourself, but up to certain limit. You cannot put in something like 45 degrees centigrade temperature, a person, you put it to 45 degrees centigrade, and you say that the person will adapt himself or herself to a comfortable situation. That is not possible. There is an upper limit beyond which it will not work. So, that is what it is. Clothing I already said. Social conditions. So, you have, if you see that Indian, there is something called the Indian index, which was developed long back, largely in this part of the country, Roorkee, CBRI, they did some work, and I think it's PhD work of Agra University somewhere. They did some work. People were subjected to, put into a certain environment, asked whether they are comfortable or not. So, from that some index have been developed that gives you a comfortable range, but gives you a tolerable range also. Comfortable range, beyond that tolerable range, and adaptation might come in someday, if more understanding, newer maths coming in, how to take care of all those. You see this management science, they use a lot of what I call logistic regression. For example, we normally in science and engineering conventionally we have been using regression where x is quantified, y is also quantified. But supposing y is a qualitative variable, good, bad, linguistic variable. In that case, there are other kind of regressions, so which are coming through, and someday we might have better answers to adaptability. But at the moment, these are additional factors not easily quantifiable. Clothing is, but social conditions and adaptation of human being, these are not easily quantifiable at the moment. So, as I said, you combine all these factors into account, and that is we call as comfort indexes, comfort indices, comfort indices, comfort index. So, that take account of these 4 main factors. Corrected effective temperature is one such index, tropical summer index is another index, and you will have many 4-hour sweat rate, etc., etc. There are a number of them, right, developed at different part of the world. CET I think initially developed in UK, and then Singapore and all this, some of them adopted, and we will discuss about that. And tropical summer index was developed in India, as I said, doing on Indian subject some experiments. So, we will discuss these two of them. Besides that, tropical summer index is in form of an equation. So, in form of an equation, and therefore, you can easily adapt it. You can easily adapt it in any Excel spreadsheet or something of that kind. CET is in form of nomogram. So, not unless you convert it into an empirical equation, you can't use them easily. So, effective temperature, this is how effective temperature is defined. It is the equivalent temperature of steel saturated environment, which will produce same effect as environment with 100% saturation and no air velocity under consideration. The point is like this. Let me explain. The statements doesn't make it very clear. It is the temperature of a 100% saturated environment with no air movement, right, which the healthy subjects will say is as comfortable as the environment under consideration. For example, you are put in a room, healthy subjects between 20 to 60 years or whatever it is, put in a room, and okay, you rate in some manner your comfort, some rating number maybe, right. Then you are subjected to another environment which is 100% relative humidity, and go on changing the temperature and say, okay, you tell me when you are equally comfortable as that. So, this one would be the effective temperature, right. At 100% saturation, the temperature which will give you same comfort condition as the environment with different relative humidity and different temperature, that we call as effective temperature. This was not taking care of mean radiant temperature and air velocity. So, then came corrected effective temperature. Now, this value of this one is 20 to 27 degree in India. Then came corrected effective temperature, which would take care of the air velocity and also the mean radiant temperature, that is globe thermometer temperature. So, this is given in form of a nomogram. Nomogram is in this one, you have these lines are for air velocities, right, and for summer clothing, this is summer clothing, like one cloth scenario, it is like this. This is dBT or GT, this line dBT or GT. This is wet bulb temperature. Now, what does wet bulb temperature represents? Relative humidity, difference between dBT and WBT. So, if your WBT is in this line, so you know the value. So, supposing this is your value, this is your value, and dBT is this is the value, you join them, and you know the air velocity, let us say air velocity is 0, then your CET is this much. CET scales are given 0, 5, 25, 30, etc., etc., etc. So, it is a given in form of a nomogram. If you know the dry bulb temperature, you know the wet bulb temperature, then you can calculate out the, you can find out the CET depending upon air velocity. For higher air velocity, this value is lower, along this direction your CET is increasing. CET is increasing along this direction. So, higher the air velocity, this is like is 2 meter per second, 3, etc., etc. Higher the air velocity, this moves along this direction. In other words, your CET will reduce with air velocity, because more loss can take place from the body. So, CET moves with higher the air velocity, CET lines are like this. These are the CET lines, this is 10 degree, 20 degree, etc., etc. This is for summer clothing, I will come back to this, and this is for knee uncovered, the Indian type of, tropical type of dresses, where up to knee is uncovered, like somebody walking in the field, as you have seen, that kind of dresses. So, this is another nomogram of the same thing, dry bulb temperature or globe thermometer temperature, wet bulb temperature, air velocity 3.5 here, and these are the CET values. So, CET values you can find out from such a nomogram. You can actually formulate them in form of equation, and I am sure if you search literature, you will find an equation giving these values as well, because these days fitting curves are not very difficult, you can always fit in. So, this is what is CET. So, CET is the equivalent temperature of 100% saturated, equivalent temperature of an environment having 100% relative humidity, no air velocity, which will produce the same thermal comfort effect as my environment under consideration, right. That is CET, and you find out through nomogram. Compared to this is tropical summer index is more, it is simpler in the sense that it is in form of an equation. So, it is actually equivalent temperature of calm air at 50% relative humidity. The 100% relative humidity is reduced down to 50% relative humidity, and then put in Indian dress, because it was done in India. Research was done in CBRI largely. So, this will produce, dress is not the summer clothing, not one cloth, and which will produce same effect. Why did they take 50%? Because relative humidity in tropical climate is usually lower. In Europe, in Europe, or let us say northern hemisphere, United States or Canada, top of it, US top part of it, you will have most of the time humidity is very high. In fact, it is drier inside the room than outside. Outside most of the time relative humidity is generally much higher, because I mean winter anyway the snow, and even summer, like some of the northern latitude you do not see the sun most of the time. Even I am not talking of the Arctic region, Scandinavian area or those ones, but even places like Scotland or the line along that line, summer you do not see much of the sun. Well, southern Europe of course you do see. So, relative humidity is pretty high. Outside it is most of the time moist. Inside, since you maintain it, it is less, but normal air situation. So, therefore, they decided to put 50%, because in Indian scenario, like tropical climates, somewhere let us say hot dry desert climate, you will have relative humidity 10 to 40%. Only in some places like coastal areas and warm humid climate, it goes to, in summer time, I mean rainy season, it goes to 90% or so. So, they decided to keep it at 50% relative humidity, and same, otherwise it is same. And then they fitted an empirical equation. So, empirical equation, the simplified form is something like this. TSI, tropical summer index, actually it was 0.33, I mean 0.3 TW wet bulb temperature. So, this is your wet bulb temperature. This value was 0.74 something. So, they actually fitted, they measure from the response of the subjects, from the response of the subject, actually they found out this TSI value, put the people to an environment, ask them to rate the comfort, put them in 50% relative humidity calm air, ask them to rate the response. When the response is same, the temperature of that 50%, go on changing the temperature of that controlled environment. When they say the comfort is same, you note that temperature. That becomes TSI. Now, you get TSI for large number of people, fit that to velocity inside that actual room, not the control room, dry bulb temperature of the control room, and wet bulb temperature of the control room. So, equation was a little bit more elaborate, slightly V minus 2 or some such thing under root, but this is simplified form is this, which is easy to remember. 1/3 it is 0.3 or something, this was 0.74 or some such thing, slightly different, approximately can be written. After all, this empirical equation, 1/3 TW, 3/4 T dry bulb temperature. So, this is wet bulb temperature, this is dry bulb temperature, this is the air velocity. These are 2 root V, 2 root V. This is what the TSI is. So, it is easily adaptable to any small calculator calculations, and comfortable ranges are, this is what it is, light summer, Indian summer clothes, that is what I said. So, comfortable ranges are something like, I will come to psychrometric chart, they actually put it in the psychrometric chart, but comfortable ranges are something like 25 to 30. So, comfortable range of TSI is 25 to 30, but they also say that 19 to 25 is tolerable. So, 25 to 30 is comfortable TSI, this is comfortable, but 19 to 25 is tolerable, and 30 to 34 is also tolerable. You can, I mean naturally conditioned, naturally conditioned, not conditioned building, naturally ventilated building, you cannot maintain this temperature, it is not very easy to maintain this. So, but you can maintain possibly internal air temperature to this. So, this is tolerable. Many people in this country may not be able to afford air conditioner and things like that. So, therefore, 30 to 34 is considered to be comfortable, tolerable, and this 19 to 25 is also considered to be tolerable. And what they have done is, they have put it in psychrometric chart, they have also put it in psychrometric chart. Okay. We will just have a quick gap and then come back again, right.